Bismillahirrahmanirrahim. Assalamualaikum and good day. In this video, I'm going to demonstrate how we are going to analyze time series data by using Jenkins method with seasonal model, or also known as SARIMA. Before that, let's recall the Jenkins model that we already learned for non-seasonal model. So this is the general form of the model which we already learned. This is for the seasonal model, which here we have the two terms, which is the order for SAR or seasonal AR and also seasonal MA. So this is another two whereby it can be expanded by using these two equations. So now we have to define PDQ for the non-seasonal and also PDQ order for the seasonal. Let's look at this example, the time series data. So let's look at the component of the time series data first. Okay, so this is the plot of time series. So we can see here that it has trend and also the increasing of the variance. Okay, so the variance is increasing, so it means that it is not constant, and also mean also not constant because it has trend. And also another component that we can see that it has seasonality. Let's look at to check the Box-Cox estimation of the data. Okay, so this is the output of Box-Cox. So the lower and upper is negative 0.4 and 0.28 respectively, and then the rounded value is 0. So here from the interval we can see that there is included the value of 1, means that the variance is not constant, so it consistent from what we have interpreted from the time series plot. So we need to transform the data by using the lambda, but now the lambda is 0. So we know that for 0 estimated lambda, we use line transformation. So we use this calculator. So we insert here the variable, okay, and then taking line, and then insert the variable, click OK. I should put here YT line. Okay, so YT is referring to the passenger data. So this is the line data. Let's check what happened to the data after we transform into line. So okay, we compare the original data, and this is the data after line transformation. So we can see that from the non-stationary variance, now the variance is constant. Okay, so no longer increasing the variance. Let's check the ACF and PACF of the transform data. Okay, ACF and PACF. So this is how the ACF and PACF looks like for the transform data. So we can see that for ACF, the lag dies down very slowly, and it has such a trend here, which is it increasing at the seasonal lag. And also for PACF, it has a significant lag here at lag 1, and also at the seasonal lag. Okay, if we observe here, the significant lag is on the 13 lag, but we still can consider that it's at seasonal lag because it's nearby the seasonal. Because the seasonal is 12, it is monthly data. So we need to differentiate the data. Okay, we try to difference the data at the non-seasonal lag first. Okay, taking the transform data, okay, at lag 1. So we transform the data and let's check the ACF and PACF for the differencing data. So this is the ACF, PACF. Okay. It's not really clear here for the seasonal lag whether it is dies down very slowly or exponentially, because now it stopped at lag 31. So we should increase the lag here. Okay, maybe we put up to 100. Okay, so this is the ACF plot. From the ACF for the transform and differencing data, okay, for the seasonal lag, maybe we can say that it dies down very slowly. So maybe we might have to difference it again at seasonal lag. But somehow let's try to fit an model whether it can be significant or not. Okay, let's interpret it one by one. Okay, first we look at the non-seasonal at the ACF plot. Okay, so here we can see that it can say that it cut off at lag 4. Okay, so at non-seasonal lag. And then we look at the non-seasonal lag of the PACF plot. So also here maybe we can say that it also cut off at lag 4. Okay, then we look at the seasonal lag. So ACF can say that you just look at the seasonal lag, so ignore in between them, or you just look at the neighborhood of the seasonal lag. Okay, we can see that it is dies down. Okay, and then for PACF, okay, here maybe we can say it is cut off. Okay, cut off. So dies down for ACF, cut off at PACF for the seasonal lag. So I suggest you to do like this, so then we can have a tentative model from what we interpret of the ACF and PACF. So ACF at the non-seasonal lag, how you interpret them, and also for the PACF, and then at seasonal lag, what is the ACF and PACF, and then we come up with the tentative model for the order of non-seasonal and also the seasonal. Okay, so for non-seasonal, just now I said that maybe it is cut off both at ACF and PACF. So what can be or possible model from that? It can be AR4 or MA4. And then for seasonal, it dies down for ACF, and then PACF cut off at lag 1. So from here it is SAR. So seasonal AR order 1. So I put here or for you to confuse. So we try on SAR4 and SAR1 first, and then we try again for MA4 and SAR1. So we try one by one. Okay, I write down the model first so that you can see it clearer. Okay, so for this ARP, okay, MAQ. So the order of AR is 4, order of MA is 4. Okay, so the first tentative model is 410 for the non-seasonal. Okay, P is 4. Okay, ARP, order P is 4. And then D is differencing. So we differencing one time at the non-seasonal lag. And then P is AR at seasonal. So seasonal AR, SAR. So is AR1. So we put here 1. And then for MA seasonal, there is no order, so 0, and also no differencing at the seasonal lag. So 100 for the seasonal. Okay, so capital here means for the seasonal. Okay, I should put here 12. Okay, so means that the seasonality is 12. And then another model is MA4 SAR1. So MA4 is order for Q. So Q now is 4 and P is 0. Okay, so P0, P0, D1. Okay, and Q is 1. And then for seasonal is the similar 100. Okay, I put also here 12, so we know that it is for the seasonal. Okay, we try to put the model just now. Okay, so make sure you take the line data without differencing. So we put differencing here and then fit seasonal model with the period is 12. Okay, so the S is 12. So just now the first is 410 and then SAR1, Q is 0 for seasonal. Okay, so let's try include the constant first. Okay, so this is the output. So from here we know that the constant is not significant, so we can remove it. And then for AR, okay, it is not significant for the second order, and also for AR4 also not significant, so we should remove the AR4 and 2, so means that remaining only 1. So we try to put again the model. Okay, so remain 1 and then exclude the constant. So this is the output as AR1 as AR12. Okay, so now both are significant. And also check for the box, aljum box. So this is not significant, this is significant, not significant, not significant. So just this like 24. So if this kind of output of aljum box, we can try on to get all not significant here if possible. If not, we can just take this one because it is not significant at here. So the important for the aljum box, we have to make sure that at least at the first 12 leg it is not significant. Okay, so we still can consider this model. Let's try the next tentative model, which is for the second one just now. Okay, this is 4, MA is 4, this is 0, MA order 4 and AR is 0. Okay, the seasonal is similar. Okay, this is the output. So MA 2 is not significant and also MA 4. So we should remove these two. So try again. So let's try 1. Okay, so now this is significant, less than 5%. So and then check for the aljum box. So this is similar with the previous model. Okay, this is not significant, this is significant. So we can still consider this. So means now we have two tentative model. Now let's try to differentiate again the data at seasonal lag. So taking the transform and differentiating at non-seasonal lag just now. Okay, so then we put here as D1. So we differentiate at seasonal lag. We put here 12. Okay. So then we check the ACF and PACF. Taking this one. Okay, so this is the ACF and then PACF. So this is the ACF and PACF after 2 times of differentiation. Okay, similarly we will interpret it at the seasonal and then at the non-seasonal lag. Okay, so first look at the ACF. Okay, now maybe we can say that it is dies down. And then for the PACF at the non-seasonal lag, maybe say as cut off at lag 1. And then look at the seasonal lag for the ACF. So here it is cut off. Okay. And also for the ACF, it also seems it is cut off. So both cut off. Then we summarize it in the table. Okay, so non-seasonal dies down, cut off. So the tentative model for non-seasonal order is AR1. And then for the seasonal, it is cut off at lag 1, and also for the PACF cut off at lag 1. So there are two possible SMA order 1. So we need to combine them, AR1 and then SAR1, and then another one model, tentative model is AR1 SMA1. Okay, I write down the tentative model, the two tentative models just now. So the D for differencing or non-seasonal is 1, differencing at seasonal is also 1. So D both 1, 1. And for non-seasonal, it is AR1. So AR1, AR1. So P is 1. So 110, 110, similar for the non-seasonal. And then for the seasonal, we have two tentative as AR1 or SMA1. So P here 1 or Q is 1. So when we combine, we have these two tentative model. So let's try to fit the model. Okay, taking just the line data. Okay, set the differencing both 1, 1, non-seasonal and seasonal. Okay, the model is 110, the first tentative model, and then 110. Then click OK. So this is the output for the first tentative model. So the both parameter is significant, and also the L-Jones box, this is not significant. Okay, so we still can consider them. Okay, so done for the first model. Let's try for the second model, 110, 0, 11. Okay, so seasonal similar, so just edit the seasonal. So 0, 1, 1. Okay, so the two parameter also significant, and all the L-Jones box is not significant. Okay, so it seems like this is the best model if we consider in the residual check. Let's look at all the 4 tentative models just now. Okay, here is for the first two model, which is the differencing is only at non-seasonal lag, and then this is the two models for the double differencing, which is at seasonal and non-seasonal lag. So this is the two models. So from these 4 models, only one model that fulfill the L-Jones box test, okay, for the diagnosis test of the residual, which is all the lags are not significant. Okay, so let's look at the residual error, residual for the fitted. Okay, so 2045, 2049, 1472, 1354. Okay, for the mean square error. So means that this is the lowest error. So we can consider this model in order to forecast the data. Okay, taking back the model. Okay, forecast, and then maybe we want to lead another year ahead. Lead 12, store forecast in 4. So the forecast will be stored in the worksheet, and then also we can choose to store the residual and the fit. Okay, afterwards we can check them. Okay, so this is the fit of the model and also the forecast and the residual. So here after when we store the residual, we can check to see whether the residual fulfill the other residual diagnosis. For example, we can check the time series plot of the residual. Okay, so here we can see that it fluctuates around the 0. Okay, so means that it is not biased. It seems not biased, but we still can check for other method. For let's say we find the mean. Okay, so we can see whether it has biasness in order to fit the model. And also we can check whether it is normal distributed or not. From the worksheet, after we store the residual fit and forecast, we can check, okay, this residual is computed by taking fit minus the ln. We can check them by using the calculator. Store it in the residual, and then the expression is the YT minus the fit. So we can compare with this one. Okay, it is similar. So this is the model that we choose just now. So let's try to expand the model in the equation. Psi pi 1 p, and then PD Q. So Q here is 0. Okay, only for P for non-seasonal. Then capital P also 0 here. And then we have differencing here 1 1 for the non-seasonal and seasonal. And then Q MA only. So this is 1. So differencing 1 12 YT, and then Q for non-seasonal 0. So Q at the seasonal is 1, P is 12, and then AT. It should be in bracket here. So now we expand this term according to this equation. So since it is only 1 here, so we stop until the first two notation here. So 1 minus pi 1b. So I didn't write 1 here because there is only 1. And then the differencing at non-seasonal 1 minus b, and then differencing at seasonal 1 minus b 12, and then equal to this minus 1 minus b 12 bracket multiply with 80. This is 80, and then we multiply this first. So I miss out this YT. I multiply with the differencing term first. So this one 1b plus b13 YT. So this one should be 12, and then we multiply these two terms. 10 b12 plus b13 plus b13 minus b14, and then multiply by YT. So this second term is, this one is just, okay, I leave it first. Then this is the same, this one, and then we multiply all this term with YT. So YT minus pi, YT minus 1, YT minus 1 plus pi YT minus 2 minus YT minus 12 plus pi yt minus 13 plus yt minus 13 minus by yt minus 14. And then the at is at minus at minus 12. And then we bring all the terms on the right hand side, leave up only yt. Okay, means that how we compose the forecast is from the equation. Right, first we can simplify the equation. Okay, y minus 1, yt minus 1, positive here, and then yt minus 2, and then yt minus 12, and then simplify for yt minus 13, and then yt minus 14 equal to the 80, and then bring all to the right hand side, positive, negative, minus 2 plus yt minus 12 minus 1 by minus 13 plus yt minus 14 plus 80 minus 12. Then we can substitute the parameter here from the output that we get for the estimated parameter just now. So this is the model just now. So we check the parameters. So this is the coefficient. Instead, the first one is pi, and then this is the for the MA terms. So substitute this value into the equation. Okay, so that's it for the seasonal model of Jenkins. So I hope that you can try on for your data for the project. So I hope you can practice to write or to expand the model by using this another three model here. I only expand this one. Okay, so this is your task for this week. Expand this three model. Okay, and then you submit in the Google Drive. I will give the assignment later, the due date. Okay, all the best. Assalamualaikum.